Hello everyone, in this video I'll be discussing previous year's questions of JAM from 2017 to 14, and that is from General Organic Chemistry, miscellaneous topics. In the previous video I have finished it up to 2018 and now I am starting from 17 up to 14, and you will get all the GOC related previous year's questions in the playlist link in the description box. Let's start. Here we have the first question. It is asking that the compounds having C3 axis of symmetry. Now C3 axis of symmetry means threefold rotational axis. It is 120 degree, or you can say 1/3 rotation of the full circle. So if I consider a circle like this, so this angle will be 120 degree. So we will try to find in which case there will be C3 axis of symmetry. So in the first molecule, here if I consider a circle like this, and if you rotate the molecule, that is in plane 120 degree. So here the C3 axis is basically perpendicular to the plane of the screen. So when you are rotating it 120 degree, this methyl will come here and this methyl will come this position. So in this way we can understand here we have C3 axis of symmetry, and it is possible because all the methyls are on the same side. Now what about the second molecule? In the second molecule, if we rotate it 120 degree, then also we will see this methyl will be coming somewhere here, but it is not exactly at these positions, right? So when you are rotating this, basically you are not getting same molecule. After 120 degree rotation, the molecule must look same, but here we are not getting so. Next molecule, the situation is just like one. Here also if I consider 120 degree rotation and the axis is perpendicular to the plane of this screen, and after rotation we will get the molecule which will look exactly same. So that is why 3 will also be having C3 axis of symmetry. So both 1 and 3, that means option C should be the correct. But why the last one is not having C3? Because see, here after 120 degree rotation, this methyl will come here, but this is above the plane, this is below the plane. So that is why there is no C3 axis of symmetry, only 1 and 3. So option C is the correct option. Among the following compounds, the pair of enantiomers. Here, if we consider the first molecule, CO2H, and the next carbon is having two substituents H and Br. But if you look at the second molecule, where CO2H is present and the next carbon is basically having H and NH2. So here bonding connectivity is not same. So 2 cannot be enantiomer with 1. Now keeping 1 fixed, if I go to molecule 3, then what we will see here? Now in this case CO2H is below and this is up. So what we will do, in plane 180 degree rotation we have to do, because that is allowed, in plane 180 degree. And when we are doing so, now CO2H will be up, CH2H here, and now Br will be here, H is here, H is here, and NH2. Now if you compare this molecule after that is which we are getting from 3 after 180 degree rotation, if suppose it is 3 prime, if you are comparing with 1, you will be seeing these two are having mirror image relationship. That means 1 and 3, these two will have these two will be pair of enantiomer. So option B will be the correct. But what about 4? Why we have already reached correct option, but why 4 is not correct, that we have to understand. Now in this case, first of all, we have to bring these two groups at up position and below position, up and down, so that we can compare with molecule 1. Now we know when you are considering any particular carbon, you can exchange 2 times. So first if I exchange H and NH2, H will be coming here and NH2 will be here. Now another exchange we have to do between H and CH2. So if we do so, what we will get? We will basically get this. The change will be like this. H is here, NH2 is here. And the same thing we will do for the other carbon. So Br and H, if you exchange its position, then again Br and CO2H, if you H, Br will be here and H will be here, right? Now if you further exchange the positions of H and CO2H, CO2H is here and H is here. Now if you compare with molecule 1, here both the hydrogens are on the same side, but they are on the opposite side. So these two cannot be enantiomer. they will be having diastereomeric relationship, but this is not possible. And one thing also I have to do here, if you exactly want to match with the first one, you have to also rotate it 180 degree. Then you will see CO2H will be coming here, CH2OH is here, HH, sorry, Br and NH2. But whatever we do, H is always on the same side. Even if you do not rotate it, actually it will be same. So only this chiral center, it is same with this molecule 1, but not the other chiral center. So that is these two are diastereomer, not enantiomer. So 1 and 3, these two will be correct. Option B. Total number of pair of enantiomers possible with molecular formula C5H12O. So first what we will do, as there is oxygen present, so there is a chance that it can be alcohol, ether, ketone. Though this from the ratio it is clear it cannot be ketone. But still if you do the calculation of double bond unsaturation, that is degree of unsaturation or double bond equivalent, then you can easily understand whether there is any unsaturation or not. Because if there is no unsaturation, it cannot be having any C double bond O. So here we will apply this formula. We have total 5 carbons, so 2 into 5 and then plus 2. We do not have any nitrogen or X halogen, but we have hydrogen. So basically what we are getting, we are getting 0. So here double bond equivalent, DBU or degree of unsaturation, we are getting 0. So double bond is not present. That means it will be either alcohol or it will be ether. These two are the possibilities. Now if I am saying that it is alcohol, then what will be the possible structures? Because once we draw the structures, then only we can understand whether there is any chiral center or not, and then the question of enantiomer arises. So first I will do it for alcohol. So I will draw the simple structure, total 5 carbon and then OH. Now there is no chiral center, so this is cancelled. Now the next thing, again I will draw 5 carbon, but now I will put OH here. Now you can find some chiral center, isn't it? Next again I will draw 5 carbon and I will put OH here. But now it is symmetric, so there is no chiral center, so it is cancelled. Now I will reduce the parent chain. I will keep it only 4. So one methyl branching should be there. Here also we are getting chiral center, so it will give us pair of enantiomer. Now still keeping 4 carbon in the parent chain, if I am changing the branching at this position and also OH here, now you will get again chiral center. So this will also give you pair of enantiomer. So we are getting total 3 from alcohol. Now what about ether? If you do the same thing for ether, now for the simple ether like this, obviously there is no chiral center possible, right? Now branching if I do, so 3 carbon in the left hand side, 2 carbon left. So here we are not getting any chiral center. Now if I keep 1 carbon left hand side, now see 1, 2, 3, 4, 4 carbon here, 1 carbon here, so total 5 carbon, we are getting chiral center. So this is also giving us enantiomer. So total how many we are getting? Total 4. 3 from alcohol, 1 from ether. So it should be 4. Now this is comparatively easier. The most stable conformation of meso 2,3-dibromobutane we have to find. Now it will be better if you draw the structure of meso 2,3-dibromobutane and then you can do it. But still if you look at this option, which one is stabler? Here all the 4 bulky groups, they are one by, that is sequentially they are coming, right? But if you look at option B, Br and Me, they are close to each other. These two are close to each other. But here we have some gap of the smaller atom, which is hydrogen. So that is why B should be more stable. But what about C? C here also we are getting all the larger groups one by one. Same problem also here. So that is why we cannot have, we cannot say this will be the most stable, right? And also if you rotate this Br here, you will see, that is rotate this Br in such a way so that it is coming at this position. So let me do it. So I am not disturbing the back carbon. Now if I rotate this bromine, so H will be here, methyl will be here. So it again proves that it is meso. So this will be the correct option. Fine. Correct statement, or it may be more than one, about the following species is or are. The first species PHCH2, then N double bond O. Now 1 and 2 resonance structures. It is mentioned in option A. Is it correct? So in resonance structures, we simply displace the pi electron or the non-bonded electron lone pair. But here we can see as if this hydrogen is, this position is changed, right? So the hydrogen which is here, now it is connected to oxygen. So 1 and 2 cannot be resonance structures, because in resonance structures we do not break any bond, right? So option A cannot be correct. What about 2 and 3? Now in 2 and 3, what is the difference? 2 and 3, the difference is hydrogen is here, lone pair is here. Again, left hand side carbon of, that is C double bond N, hydrogen is still there, but lone pair is here. So here H and OH are on the opposite side, but here it is on the same side. So whenever we have this type of situation, it is basically syn anti isomer, which is under diastereomer. So if we consider the broader definition of diastereomer, those stereoisomers where you do not have any mirror image relationship, so syn anti, it should be considered as diastereomer. So these two are not resonance structures. So B cannot be correct. This is not correct. C is fine. C is correct. And the relationship of 3 with 1. So 3 with 1, if we see, 3 is a tautomer of 1. So tautomer is basically where we break bond. So in this case, as we are breaking this carbon-hydrogen bond and we are getting a new bond between oxygen and hydrogen, that is when we have OH group, so it is tautomerism. So 3 is tautomer of 1. So C and D should be correct. Number of all possible isomers for the molecular formula C6H14. Now from the ratio we can understand it is alkane, because it is CnH2n plus 2. So here n value is 6, 2n means 12 plus 2, so it is 14. So whenever we will have to draw all possible isomers, what we can do, see here total number of carbon is 6. So first you can draw the parent chain as 6, and then you draw the parent chain 5, then you will have to place some branching, then you reduce it to 4 carbon parent chain, then branching will increase. So in this way, one by one, starting from 6 to 5 to 4, decreasing the parent chain carbon number, we can find all the possible isomers. So we have to do it in this way. Here when it is hexane, total 6 carbon in the parent chain. Now for pentane, that is 6, total 5 carbon in the parent chain. You can have two different types of branching, methyl branching, either at 2 position or 3 position, and then keeping it at 4 carbon parent chain. Now you can have two branching, but both the methyl you have placed in the same carbon, or at carbon 2 and 3. Okay, so 2,3 dimethyl, 2,2 dimethyl. So how many we are getting? We are getting total 5. Specific rotation of R enantiomer of a chiral compound, it is 48. So when it is R, it is 48. So it means what? When it is S, it must be minus 48. Okay. Specific rotation of a sample of this compound which contains 25% of S enantiomer. That means 75% is now R enantiomer. So you have mixture of 25% S and 75% R. So R is present 75%, S is present 25%. And overall, what will be the specific rotation of the mixture? That actually we have to find. So what we will do? 25% of S. That means it should be multiplied by 48. So this is for S. Now 75% is for R. And in this case, it should be multiplied by positive 48. Now if you do the calculation, you will see it will be 24. And overall it will be positive. Why? Because 75% is R and R is positive. So ultimately it should be positive. So this is one way you can solve this problem. Answer is 24. But another way also you can solve this problem. And what is this another way? Suppose EE, we know that specific rotation of mixture divided by specific rotation of pure enantiomer. Okay, so in this case this EE, that how that we can understand, because 20% and 75%, that means 25 will cancel 25 out of 75, so there will be, that is EE value, ultimately it will be 50. Okay, so specific rotation of the mixture, that is actually the answer we will get. So you have to place X value here because we do not know it, 48 and 100. Now here from this formula also you can find out that it will be 50 by 100. So you are getting the same answer. But for me, I think the previous method, it is easier to understand, because in this case, that is in the second way, first you have to find the EE and then you have to put it in this formula. But whatever it is, whatever way you want to solve it, it is up to you. But both methods are giving us same result, 24. Among the following, the number of molecules possessing C2 axis of symmetry. Now C2 axis for the first molecule, if I am placing axis like this, now this axis is on the plane of the screen. So when you are rotating it, that is considering this axis, this methyl will come here and this will be, that is 2 methyl, their position will be exchanged, and this methyl, it will be fixed. So here we have C2 axis of symmetry. Similarly for the second one also, it is symmetric structure. If you place an axis through this point, that is it is going through this point and coming then that is below. So if you rotate it, you will see these two carbon, now it will be exchanging position with these two, then these two methyl will exchange position with each other. So here also we have C2 axis. Now for the third molecule, if I am drawing axis on the plane of the screen and if you are rotating it, H, these two H, their positions will be exchanged, Cl, their positions will be exchanged. So you are getting a molecule which will look same. So here also we have C2 axis. Now for the fourth one, here we have that is this type of substitution at ortho position. This is biphenyl system. So what we will do, if you look at this molecule from this position, okay, then what you will see? You will see these two methyl groups and these two, which is up and down, it should be like this. Now when you are drawing this molecule and you will get axis, so this is diagonally through the central carbon, and you can understand this axis only when you are looking at this molecule from this side. You can also do it from the other side, but in this C2, when you are rotating this molecule, remember this axis is diagonally through the central carbon. Though there is no central carbon, this is true for this alene type of system, but central carbon, by central carbon I mean to say this, suppose somewhere here we do not have any central carbon, but somewhere, suppose the center is here. So when you are rotating it, you will see these two methyl, they will exchange their position, and same is also true for here. So for this type of system, we also have C2 axis. Now I will also do it for the last molecule first, because they are almost similar type of situation. Okay. Now if you look at this molecule from this side, so what you will see, H will be left hand side and chlorine is here, and for the back carbon, this one. So here also from the central carbon, that is this carbon, if you imagine any axis diagonal through the central carbon, you will find C2. Then so here also we have 2,3,4,5 dimethyl thiophene, 2, 3, 4, 5. So these two are the positions. We will have C2. For CHCl3, now there is no C2. You have C3, but C2 is not present here. Okay, so this is not possible. What about BF3? Now for BF3, the situation is same. It is planar molecule. So whatever we have seen in case of the first molecule, same type of you can put the explanation. So if you have any axis like this, which is on the plane of the screen, and if you are rotating it, this upper fluorine, its position will be fixed, but these two fluorine, their positions will be exchanged. So except CHCl3, in all other cases we are getting C2 axis of symmetry. So that is why answer should be 7. Structure of 2s3r 2 amino 3 hydroxy butanoic acid. So let's first draw this molecule. If we draw this molecule, this is 1 2 3 4, 3 position hydroxy, 2 position NH2. That means in all these molecules, if you see, this is 1 2 3 4. So bonding connectivity is fine, and that is also true for C and D. Now we will find out R and S for the first molecule. NH2 you have to give more priority, so I am now considering the chiral center 2. 3 we will do later. So here first is NH2, after that CO2H, and then this rest of the group. So this is 1, this is 2, and hydrogen is 4. So 1 2 2 2 3. It is basically anti-clockwise, but H is on the horizontal axis, so that is why horizontal bond, that is why it should be R. Then for the second chiral center, this is number 1. Now this whole group will be having priority number 2. This is number 3. So 1 2 2 2 3, we are moving clockwise, but it should be S. So what we are getting? We are getting 2R 3S, but it should be exactly reverse. So just look at any other option and try to find out in which case the positions are reversed, and that we can find in third molecule. And third molecule, see here NH2 and H, their positions are reversed. Also true for H and OH. Basically A and C, if you look carefully, they are mirror image to each other. So it is clear it must be 2S 3R, and this is the correct answer. Okay. Now this is easy to do. Homolytic breaking of CSCB bond is easiest in. So after homolytic cleavage, suppose you are doing some homolytic cleavage for AB bond, what you get? You get single electron radical. So in which case the radical will be maximum stable? Obviously in the last one, because when you are breaking it, you are getting Me3Ca and another Me3C B dot. So in this case, because of 3 methyl groups, if you consider inductive effect, hyperconjugation, so everything is supporting this radical more stable. So after homolytic breaking, the radical that you are getting, based on the stability of that radical, you have to find in which case it will be easiest, because when the stability of the radical produced after bond cleavage is stable, obviously that will give you that is the molecule you can do the breaking easier way. Okay, so D should be correct. Which one among the following molecule is chiral? Now for the A, it is allyne system. Now if I look at this molecule from this side, this 2 chlorine, so this bond I will draw as bold, and you are looking from the left hand side, so this H, now it will be left hand side of yours. But whatever it is, you can see if you are cutting this molecule, sorry, not this axis, I have done it wrong. If you are cutting this molecule along this plane, okay, then both sides are equal. So whenever you have this type of substituents, that is one side you have same substituents of allyne system like this, then you will get that is, if you are basically cutting this molecule along this plane, then both half will be equal, right? So this should be having sigma plane. This is not chiral, so this is not our correct answer. Now what about B? In case of B, we have 3 cumulative bond. Now when you have 3 cumulative bond, it is basically odd number. Here it is only 2 double bonds. It is even cumulative double bond. So even and odd, based on that you can understand whether it will be optically active or not. So when there is even number of cumulative double bond with different groups on terminal carbon, so here we have different groups, then it will be optically active. But that is for even number. But in this case we have odd. Total 3 bonds are there, cumulative double bonds. So when it is odd number with different group, it will be ultimately optically active. Because ultimately you will see all these 2 chlorine, 2 hydrogen, they will be in the same plane. You can compare the situation with this molecule as if A and B, H and Cl. So you can see ultimately this A and B, they are on the same plane. But if you are having the molecule only up to this point where you have only 2 double bonds, that is even number, then the groups that will be at this carbon, these 2 groups and these 2 groups, they will not be in the same plane. So that is why it will be optically active. But in this case, it is odd number, it is inactive. So this is also not correct answer. What about C? Now in case of C, unlike A, where you have two similar groups, now you have not similar groups. So if you are looking at this molecule from the left hand side, you are getting Cl and H, and this back carbon, these two substituents. Now chlorine is here and hydrogen is here. So in this case, C2 axis is possible, but you do not have any sigma plane. So you cannot cut the molecule into half. So this should be the correct answer. And the same C, if it is correct, then D is not correct. But why? Now the situation of D, it is just like the case as we have seen in A. So when you are looking at this molecule from this side, Cl is here, H is here. But Cl, Cl. So if you are cutting this molecule along this plane, which is perpendicular to the plane of the screen, both half are equal. So that is why here also we have sigma plane. So correct answer is third one. Correct orientation of dipoles in pyrrole and pyridine. So for pyrrole, just compare it with its saturated counterpart. So this is unsaturation, this is saturation. So when there is only sigma bond, what happens? Nitrogen is electronegative. So the sigma moment, that will be towards this side. But when you have pi bond, this type of resonance is occurring. So pi moment is basically opposite. Okay. So ultimately what happens? This sigma moment and pi moment, these two are reversed to each other, and pi moment ultimately wins over sigma. So ultimately, in case of pyrrole, because see here in this molecule I have not drawn the double bonds, but this type of sigma moment will also be operating in pyrrole, because sigma bonds you still have, but pi moment also you have to consider, which is overcoming this sigma moment. Ultimately it should be towards upper side. That means any of these two should be correct option. What about pyridine? In case of pyridine, here also you can compare with its counterpart, where you do not have any pi bonds. Now here, unlike pyrrole, this lone pair is not part of any resonance. So the sigma moment, if you consider, that is towards nitrogen side because of its high electronegativity, and here also, that is as resonance is not possible, so pi moment, that question does not arise, right? And here sigma moment ultimately you can consider, and that is why its direction will be downward, and that you can find in option A and option D. But in D it is not matching, so that is why first option should be the correct one. Specific rotation of freshly prepared aqueous solution of 1 and 2. So 1 is 112 plus 112, and for the other one, that is 2, it is plus 18.7. Now see, these two are basically all the chiral centers, only this chiral center it is different, where OH is axial and equatorial. Otherwise you will not find any difference in the other chiral center. But whatever it is, whatever is the relationship, here values are given 1 to 18.7. On standing, the optical rotation of aqueous solution of 1 slowly decreases to give a final value. So these two are the extreme value when it is in pure condition 1 and 2. But when you have some mixture, 1 and 2 mixture, and ultimately you are getting 52.7, then this information is given, and we have to find under this state of equilibrium what is the ratio. So we have some mixture, but what is the ratio of these two, that we have to find. Okay. So for 1, suppose I am considering this is x. So for 2, if total amount is 100%, it must be 100 minus x for 2. Now for 1, it should be x multiplied by 112. Then 100 minus x, that should be multiplied by 18.7 and divided by 100, and you are getting 52.7. Now if you solve this problem, you will get the answer of x. It will be basically 36 point something. But if it is so, sorry, not y, basically you can also consider it as y. So for this, that is 2, it should be 100 minus x. 100 minus 36. Okay, so 100 minus 36, it will be 63. So ultimately what we are getting, this is 36 and this is for 1, this is for 2. So we have to find the ratio of 2 divided by 1, and that should be 63 divided by 36, which is basically will give you 1.75. So this should be the correct answer. Fine. So that's all in this video. Thank you for your time.